All right, you ready to move on to the next one?
Sure. Okay. So the next one, we've got our expectation back. That makes me happy.
Yay.
So we got our expectation back. But now what we're doing is the next thing that'll happen is rather than doing the best action from that point on, we will take an action, we'll take sort of the average over all possible next actions,
Mm-hmm.
but give more weight the better the action is, if I remember what your row of ORD actually does.
That is a nice way to do it, but this is not written to be that way. It's just weighting by the ranking. So it could be that we put higher weight on higher ranked things, but it could be we put higher weight on lower ranked things too. So this is a very
Oh.
kind of a very general expression. But you're right. I mean, this would be useful in the case where it's doing some kind of, I don't know, maybe a generalization of epsilon greedy exploration,
Mm-hmm.
right? The idea that we're going to, with highest probability, choose the max, and with lower probability, choose things that aren't the max. So it generalizes that idea.
Right. And so actually that would be nice because one of the things about the way we go around learning MDPs and do Q learning and value iteration is we kind of assume we're always going to do the next best thing. But since we still have to do exploration as well as exploitation, that isn't actually what we do. So this would allow us to do exploration.
Well, it's not that it's allowing us to do exploration, it's actually defining the values so they incorporate exploration into them.
Right.
So one way of thinking about what this is an exploration sensitive MDP.
Right. That's exactly what I was going to say.
Oh, awesome. Well, just to finish this thought, the values that you define for the states include in them the probability that you might take a non-maximum action. That's the sense in which the values are exploration sensitive. We can explore in, say, Q learning and still use this first update rule to try to figure out what the value is for the best policy. This is actually trying to figure out what the value is for the policy that is exploring.
Right. And in particular, the policy we're going to follow as opposed to the policy we could follow.
Yeah, that's a good point.
Right. I think that's important.
Yeah, so this is kind of neat because unlike regular Q learning, it's actually figuring out the value. It's on policy. It's actually figuring out the value of a policy that we might really be taking. Whereas if we were to literally always take the max, we won't learn the right value in the case of Q learning, right? Because we're going to get stuck not
Right.
exploring.
Okay. I like that. I can't think of a better name, though. Are there any other names for this besides exploration sensitive?
Well, as I said, it generalizes max and min. You can one of the things that I really like but have absolutely no use for is that you can imagine an update rule where you always are trying to choose the median action, kind of not too good, not too bad, middle of the pack. I guess it's kind of like the decision process for people who just want to be mediocre and not stand out. So I'll say mediocre.
Mediocrity sensitive MDPs.
And there's another case where I found a use for this, which I think is kind of interesting. So imagine that we've got a huge action space where actually computing this max is going to be difficult.
Okay.
So instead of actually running through all possible actions to compute the max, we're going to take some random sampling and then just compute the max of that random sample. So does that make some sense as an algorithm? Like instead of taking the max over everything, we'll just take a max over a handful of things.
Sure, that makes sense if you have, for example, an infinite number of actions.
Yeah, that's right. Or even just a very large number of actions. The first time I heard about this was in the case of an MDP that was being used to define scheduling actions for the space shuttle, back when there was a space shuttle. And there was just so many of them that going through them was intractable. So this is Tom Dietrich's work. He actually randomly sampled some of the actions and then chose the best among that sample. So what that gives you actually is there's some probability you will choose the actual max, but there's also some probability that you miss the max and instead get the second largest out of all the actions. And there's some other probability that you get the third largest of all the actions. It's more likely that you get higher ranked actions than lower ranked actions, right? Because of the subset that you choose, you're always taking the max of that.
Mm-hmm.
But it's not going to be with probability 1. And so what you end up with is just some kind of distribution over the likelihood of choosing the max and the second highest and the third highest and so on. And this equation generalizes that idea and shows that if we use this as our update rule for something like value iteration, we get a well-defined answer, right? This will converge to something. It's just a little bit hard to say exactly what it converges to. It's not the best possible policy. It's more like the policy that we get when we always choose the best action from a random sample.
Right. But if there are a bunch of pretty good actions, then you may not get the optimal policy, but you'll still get a pretty good one. It's like being satisficing as opposed to satisfying.
Ooh, yeah, I would accept satisficing as an answer for this one. That's cool.
Okay.